Hello, my name is Shubhrana. My teammates are Reddy, Surya, and Darshan. And this is the video to show the net FPGA working of a multi-thread RISC-V processor. So currently our processor is quad-core threaded. So basically we have four threads running for it. And basically I'll start off with showing this assembly. So basically we are doing sorting program for five different numbers in all the four threads. So you can see the thread 0, thread 1, thread 2, and the thread 3 assembly text file. So basically in all the four, basically the numbers, if you see, the numbers are different, but we are using the bubble sort code only. So basically in this we are storing them in the, these are the so as the numbers are different, we are also storing them in a different locations memory. These are basically stored from 0 to 4 location and sorted accordingly. These are in the next locations, then these, and then so, and then again, if you see this main structure of the code, this is same, only if you see this only the places, because these numbers will be stored at different locations. So when we pick these numbers to compare and then do sorting based on if it's lesser or not, and then storing it back, these offset values are different. The rest of the code is basically generated the same only. And yeah, again, while just loading back and checking them again, because as they were loaded in different locations, we are taking it back from different locations of memory. And yeah, so this is our assembly code, and based on our this already in previous video shown, now we have already a Python script which generates a binary file for this. So if you can see, the binary was generated, and our PC, so basically our instruction memory is divided into four different sets for the four PCs. So if you see, this is the COE file for which our instruction memory is loaded. So you see, this is the thread 0 loaded, and it's loaded till here. And then so basically this is the first zeroth location of instruction memory, right? So this is 3. So next, like, it's because the depth is 512, so each section has a depth of 128. So next one should be after a, so basically 0 is at 3, 128 should be at 131 location. So if I go to location 131, you see again, yeah, so you see the next for PC, the thread 1, this is the binary code which is being added. And meanwhile, in parallel, I'll just load our. So if you see, this is loaded. This is for PC1, and then again we have 256. So added to 3 and 259. Yeah. So if you see, this is the thread 2, and then the last thread will be at 387. Yeah. So this is the next thread. So everyone has a equal set of 128, and we are only using like 30. This bubble sort happens only in 30-bit. Next instructions are 0. And we have, so basically this, if you can see, in terms of this, in Darshan's video he has covered it, but I'll still show this little part. So we already have this four pieces, right? So that's why we have differentiated. So based on the thread ID which will be shifting from 0, 1, 2, 3, 4, these out of these four different PC, one PC will be selected for the PC out, which is going to the instruction memory to read the current instruction. And every PC is basically enabled. So if you see, this is from the 384th section, and it's going, and it's counting from the 100 section, and similarly this is from the 080, and then this is from 0th location. All right, and basically this is our thread ID. Okay, so it's incrementing, and yeah, so if you see, this is Mercs PC which is going, Mercs PC which is basically nothing but basically the PC out if we are not using the software interface. Correct, and I'll show in my NetFPGA design. And then ping. So if you see, we are able to ping the design. So design is working, and if you can see, so basically our design is, if you see, we have constructed four different PCs, and using those PCs we are going through these four different assemblies. And I'll just run while so basically we have already this logic analyzer. You see, run this script. So already I've run the simulation. If you see the simulation part, okay, yeah. So as you can see in the simulation, just like in the simulation, we got the final results. Like these were stored back, and if you can see in as like the initial PCs, so this would be going from 0, 180. So basically 0, 128, 256, 384, then 1, 129, 257, 385. We should get something similar values in this logic analyzer. We have made a logic analyzer of depth of 256. So for the first 256 cycles, it will store the values. We plan to basically increase the depth of the logic analyzer for future code so that it takes into account a bigger and extensive code or assembly number of assembly instructions to basically store and so that we can verify and check them. And yeah, so here from here we can verify this comparing this and our logic analyzer values. So basically in logic analyzer we are basically reading these values, the PC values, and we are reading this new instruction which is already coming from the instruction memory. So you can see whatever is in the simulation we can match and we can confirm if our design is running fine. So if you see already this analyzer data text file is already there. So if we go to the top, so if you see like again location 1 basically 0, 128, then 256, then this 384, and then one is, so this PC is going in proper in sync. And similarly if you see the instruction, if you can see new instruction, yeah, so if you see it was all zeros, then it went to 9600513, A200513. It's again here the same thing is there. And then similar to this if you see the values, basically the values if you can see it, where is my assembly? So if you see 150 should be loaded first because this is thread 0 first instruction, and then 162, right, when we are storing this in the memory and all, and then 174 and then 186. So similar values you can see 150, this is 19 into 9 into 6, that is 144 plus 6 150, 10 into 6 160 plus 2 162, uh, and again 10 into 16 160 plus e which is 14 174. So 162 174 and 150. So I'll show the final values. So I have the script to basically run all the locations of memory. Sorry, memory analyzer. Yeah. So based on this, it will print out the final locations of memory, whatever is stored in the memory. We'll have those final locations. So I'll show once. We have shown this script in the previous video also, but I'll just show once again. So again, using the software command as I showed in the Verilog. So using that interface, we are basically using this to basically read the output of the memory because we have given the software command enabled. First bit is turned off, and so basically first this is turned on and the second bit is turned off, and then this will be data from data memory. And you can see again, yeah, software command register basically the value to access data memory in read mode. So rest bits are 0, the first bit is only set as 1. So we are doing read write, and then basically we are giving this because this locations in hard data. The first two 512 locations are instruction memory, and then from that 512 to 768 is for the data memory. If you see, okay, and yeah, if you see, so if you see the first locations we are giving to hard data, and then the next locations is stored in the data memory. So initially we are storing this, and then we are doing this, and then if you see, yeah, so read pointer we are reading the all the basically we're giving all the this read pointer 512, so basically reading all the locations of data memory. So basically 0 to 250, all 256 location of data memory, and then the basically whatever value is there we are reading that and basically storing and printing in a file. So I'll open that file to just show the final values. And data memory.txt, yeah. So if you see for the first 5 numbers, if I show you the assembly, yeah, So these were the first files in the thread 0. These were stored and these were in the 0 to 1, 2, 3, 4 location. And we should have in 0, 1, 2, 3, 4 location 14, then 100, then 150, then 123, then 150, and then 190. So if you see 0, 1, 2, 3, 4 location, we got first 14. Then this is 6 into 16, 96 plus 4, 4. That is 100. So again proper. Then 7 into 16 is basically your 112, and then your B is 11, so 123. So if you see 123 was the next value, then next value should be 150 and final 190. So 16 into 9 is 144 plus 6 is 150, and this is 11 into 16 is 176 plus 14 is 190. So this is proper. We sorted this properly. Again, same. So for 10 to 14 locations, if you see, next thread had to evaluate and store at location 10 to 14 in data memory, and basically this was proper. So this was from 10 to 14, and we got look values like 1A, 70, 9A, and A2. So these were the values, and then yeah. So if you see, 1 is 16 into 10, 26. 16 plus 10 and 26 to 26, and then this should be another value should be 112. So 112, if you see 7 into 16 is 112, nothing else. So you can check all the values and you can see it. 1, then 7, then 9, then A and the C. So it's in like increasing order. Then again from 20 to 24, again everything is sorted in increasing order, and this 30 to 34, everything is. So we can see like all the threads are working properly and we are able to see the correct values in memory. So our quad core multi-thread processor, quad core threaded processor is working fine. That's it for the video. Thank you so much.